thank Suzanne Keenest-Brown for being here to support our webinar and introduce our presenter. Suzanne, I'm going to turn the webinar over to you so you can introduce the topic and our presenter.
Okay, thank you, Sean, and thanks everybody for tuning in today. I am happy to introduce our speaker today, Jessica Phillip, or maybe you've heard her name as Philippe or Felipe. She accepts all versions of her last name, so the good news is you really can't get it wrong. Jessica is a soil scientist and GIS specialist in St. Johnsbury, Vermont. She's been an innovator and early adopter of digital soil mapping in her work during her entire 15-year career as a soil scientist with NRCS. She is recognized as a lead DSM practitioner and for her practical application of digital soil mapping in soil survey. She has contributed her expertise to successful raster soil survey projects such as Essex County, Vermont, which was the first raster soil survey published, and the Boundary Waters Project in Minnesota. She has been a very active member of the DSM Focus team since it began and continues her leadership on the team as co-lead along with myself and Jim Thompson. Today, she's going to give us an overview of her current raster soil survey project on the White Mountain National Forest, where she is combining machine learning and knowledge-based classification in a unique way to meet her project goals. So I'm really excited to hear about the progress on this project today. I think people will find this very interesting and innovative way of combining different methods of classification within the context of DSM and soil mapping. So Jess, I'll turn it over to you.
Okay, thank you, Suzanne. And she's right, you can say my name however you want and I'll still answer. But the key is that there's only one L in it, so if you're going to email me, make sure you pay attention to that. So I am going to talk about integrating machine learning and knowledge-based soil inference classification in the White Mountain National Forest. And really what I'm trying to do is just give another example. You know, if you've been tuning into these webinars, this isn't the first example of digital soil mapping in practice. And my goal is to show that there's not just one way to do DSM, and sometimes something changes within even the same project that means that you have to adopt a new technique or just kind of adapt what you're doing to whatever your conditions are. So the White Mountains have been a perfect example of that, and I'll show why. But like Suzanne mentioned, this is not our first digital soil mapping project. We were comfortable with doing DSM when we started work in the Whites, but things have continued to evolve, and I hope to show you that that is relatively easy to do and give you some really pretty pictures to look at while we're at it. These pictures are of digital soil mapping. You'll hear me say this again, but digital soil mapping is soil mapping, so a lot of it looks really familiar to people. And I will also say that a bunch of these slides come from our digital soil mapping trainings, so they might look familiar to some people, and this is also a plug that if any of this is really interesting and you want to learn a bunch more, then come see us at our trainings. We have a bunch of them. So who am I? Suzanne pretty much covered it, but I am a soil scientist. I've actually been working for NRCS for 16 years now. I started as a soil conservation aide and pretty rapidly saw that the grass was greener on the soil side, and I have not once regretted my decision to swap over. But I was super lucky to be able to get a position in an office, not only in basically my hometown, but in an office that was working directly with Dartmouth College to develop the ArcSIE Inference engine software, which is now loaded on pretty much every soil scientist computer, and it's something that we teach lots and lots of people how to use. So I have always been doing DSM basically my whole career, and because of that, I've been super lucky to not have to knock on any doors. I never had to use a stereoscope other than to prove that I could see in stereo to my supervisor. But I have dug a lot of holes, and I am a huge proponent of field soil scientists being the experts who are doing the digital soil mapping. I don't think it should be done by an external force. I think we are the people that really understand the soil-landscape relationships, and that is what makes DSM successful. So just a little bit of, kind of what is digital soil mapping. Again, if you've been tuning into these, then you've seen a lot of this, but I think it's important to always kind of go back to what we're talking about. And digital soil mapping is soil mapping, but it is based on the quantitative relationships between spatially explicit environmental data and field data. And this is what makes us able to produce a reproducible and consistent result, and we can also include measures of accuracy in that, which is really great. So we do this via basically an expansion of Jenny's model that is brought into the context of digital soil mapping. So, we're still defining the soil landscape model that soil scientists have had in their heads for many years. We are just doing that quantitatively by looking at the relationships between our soil classes that we're trying to predict and environmental covariates that tie to those soil forming factors. And this is now an explicit spatial prediction that allows us to incorporate measures of accuracy or uncertainty. So, this is something that's a little bit different from traditional soil mapping and Sergo products. We were never able to really well establish the accuracy of a Sergo product, and we can do that with DSM raster products. So that's pretty cool. One of the big differences between conventional soil mapping and digital soil mapping is that in conventional soil mapping, we spend a lot of time focusing on where the boundary is between two soils. If you're out mapping, you're kind of wandering around really looking for where things change. So a lot of your resources are spent in those areas. But with digital soil mapping, we actually focus on defining the central concept of the classes that we're trying to map. And just by nature of a raster soil map and using all these environmental data layers, the variation between classes just kind of naturally gets expressed across the landscape. So we're able to spend our energy on defining the things that we know and go from there rather than trying to figure out what we don't know. So there's a lot of different ways to kind of define that central concept. There's lots of different classification techniques, and for the White Mountains, right now, we're using a couple of those, so I'm only going to talk about those two. Again, we have a really good class, the Introduction to Digital Soil Mapping, that goes over a whole bunch of other methods of defining central concepts, really. But what we are using is the random forest algorithm, and that's done in R, and I'll give you a little bit more details on that in a couple minutes. But we're using that in combination with knowledge-based soil inference using the ArcSIE software. And both of these are perfectly good ways to define classes. They both require knowing what the classes are up front, so they're both forms of supervised classification. But they each have pluses and minuses for using them. Using random forest models requires a bunch of upfront field data, whereas knowledge-based classification doesn't necessarily require that much upfront field data and is able to capture what soil scientists know about the soil, but it's very time intensive. So it's something that when we had to look to be more efficient, random forest was a way to help us get there. And I'll explain that in just a second. So let's talk about our project area. The White Mountain National Forest is about 800,000 acres, located mostly in New Hampshire and a little bit in Maine. It's part of MLRA 143, and it has the Presidential Range, or kind of the high peaks that run up through there. And of course, it's a national forest, so the land use is mostly recreation and forestry. It is, for us, it's considered pretty remote, but it is nowhere near as remote as a bunch of the wilderness areas out west that we're also doing DSM projects on. This has hiking trails all over the place. There's a couple highways go through there, so You know, we may have to hike for a couple hours to get somewhere, but we don't have to go camping for 2 weeks to be able to do field work. So that's good. Our office, like I said, has been kind of at the forefront of the transition to digital soil mapping as far back as 2005, maybe even before. That's when we started working with Dartmouth to help develop SIE into something that was operational. And through that process, we really perfected the knowledge-based soil inference process in the Essex County, Vermont soil survey. And we kind of began transitioning that process to the White Mountain National Forest a few years ago. But along the way, we have continued to learn new techniques, and we always strive to employ the most scientifically rigorous processes that we can. But the reality is that we do have acreage goals, and we feel an obligation to produce the best possible soil maps that we can to meet customer needs. So, you know, we are not pressing a couple buttons and having an output and saying, here's the result, you know, who cares how good it is? We have a map. We try really hard to make as detailed as possible, as accurate as possible maps. And honestly, you know, our customers kind of expect that from us after the Essex County experience, but we are continually having to adapt how we do that. This is the team that did the Essex County survey for the most part. There were 4 of us working nearly full-time. I mean, we were all working full-time, but the Essex County project was basically our only priority at the time, if I remember right. I'm sure there was other things going on, but this was really 4 people working all the time on Essex County. And I think that was about 400,000 acres, and it took us 4 or 5 years to do. Now we are down to 2 people, and of course, just like everybody, we have a whole lot of competing priorities and other major projects going on. So again, we've had to look for ways to become more efficient. And our general digital soil mapping process that we employ hasn't changed. What we go through is still the same. It's just the actual methods that we're using at various points along the way that have been adopted and adapted. So, you know, the first thing that has happened is we have been responsible for our data processing the whole time. You know, DSM uses a combination of terrain and spectral derivatives. For us, it's very terrain driven. So I have been processing the LIDAR since like 2005, and it was actually just about a year ago that we got LIDAR for the whole White Mountain National Forest. So our office has been responsible for making that into something usable for DSM. And then the first thing that we do is we stratify the landscape by parent material, and we have a whole big process that entails that I'm not going to go into, but the important thing is that we stratify by parent material and then treat each individual parent material separately for modeling purposes. You know, different soil forming factors might be at play in different parent materials, and so different environmental layers are important for modeling. So that's kind of how we have decided to approach it. Rather than build one big model for everything, we do that stratification first, and it really seems to, you know, I still have some testing to do on this, but as far as accuracy numbers go, it kind of keeps things at a little bit higher baseline level if we're not screwing up the parent material to start with. But that's a side note. So within each parent material we build a model, basically a Catena-based model, and the steps involved in that are knowledge extraction, and I mean that either by just us soil scientists, experts sitting around and saying, hey, what do we know about these soil classes, and what do we want to make sure is captured in the final map? And also that's field data collection, and there's a bunch of different ways to do that, but you know, basically it's knowledge gathering and extraction, choosing which environmental layers are going to be important, so which terrain or spectral derivatives are important for being able to illustrate the soil landscape model, and then we actually make the predictions. And for us, traditionally, that was using a knowledge-based process. which is very iterative. Every time you dig a hole in the ground, you have added to your knowledge, so you may go back and refine the model, but that prediction can also be something like random forests or other machine learning techniques. And regardless, we then do field verification to see how the model performed and then make adjustments as needed. And so that's an iterative process. Again, it can, especially in the knowledge-based side of things, it can be iterated basically forever. You know, there's always something to improve. So at some point you have to call it quits and do some post-processing of your results. That this is an initial survey, so we do post-processing to meet whatever standard is necessary, and this is an initial, so it will have to go into Surgo. So we will post-process the raster into something that can be vectorized and made into Surgo, and then we do correlation and publication, which, you know, that process is not that different than what we are used to doing. So like I said, we do a Catena by Catena modeling approach, and the first thing we do is stratify the landscape into parent materials. The green you see on this map is identified as dense basal till, and that's where we had our first model. That's what the Essex County model was, so we kind of translated that into the White Mountains, made adjustments, and applied it everywhere that there is basal till. Side note, we have not mapped the parent materials in the whole forest yet, so this is an incomplete map, but it shows sort of the distribution of what the parent materials are. So all of the green stuff and more of this that just hasn't been mapped yet has an approved model that has gone through the whole regular process of field reviews, and it was approved by the regional office about a year ago. So then we moved on to the next parent material, which is ablation till, and that's where we're employing this hybrid approach that I'm talking about today. So all the pretty pictures you'll see in a little bit are all from ablation till. And then we have a bunch more parent materials too that I'm not sure exactly how we will map them. You know, I anticipate using basically the approach that I'm talking about today, but things do change sometimes rapidly. So the important thing is that we try to treat each parent material with respect to its independent soil forming environments. So let's go back to knowledge-based digital soil mapping. That is how we did the basal till, and it's part of what we're doing in the ablation till. And the whole purpose of knowledge-based DSM, and really any DSM, is to extract the soil landscape model that lives in an experienced soil scientist's head and turn it into something that's consistent and reproducible. And for knowledge-based DSM, that means we're putting in our knowledge and environmental data into this soil inference engine. That's the user interface for it. It's really simple. And what comes out are fuzzy soil membership maps. So we define what we know about soil, and this can be done in the form of a rule like this, or via point data, which I'll get into in a little bit too. But you know, basically we know things about where certain soils occur, and we're able to tell that to the computer. But the thing that's good about inference is that we are able to, instead of define really hard breaks, you know, if let's say we know that a certain soil occurs between 200 and 600 meters of elevation, that doesn't mean it doesn't occur at 199 or 601. So with fuzzy soil inference, we are able to kind of drag that curve out and make a gradation that better represents the continuum that is soil. And that gets us a little bit closer to being able to map reality. We'll never be able to really map reality, but we can approximate it pretty well using this process. And like I said, what comes out is a fuzzy soil membership map. So looking at all of the environmental data layers that tie to our soil forming factors, the program is able to tell us everywhere that is similar to the defined soil forming environment and give a high fuzzy membership at that area. And this is going to be important in a few slides when you see how we've combined this with a classification from random forest. So knowledge-based digital soil mapping, you know, if you look back at the little diagram of what DSM is, and it's a combination of training data and covariates fed into a predictive model, and out comes a soil map. When you're talking knowledge-based DSM, that training data doesn't necessarily have to be point data. But for this project, it is point data, and you'll see why, because we can use either cases or rules to define that soil landscape environment. And like I said before, we have, if you want to use a machine learning method, you really need a bunch of actual point training data to be able to do that. So what happened was we finished up our basal till model, which was entirely knowledge-based, and we started moving on to the ablation till model, and I started looking at how much point data we had in the forest, and turns out we had quite a lot. We had 800, this is a snapshot actually that I did yesterday. We have 849 existing data points that have a soil series name attached to them. So these are the points that I consider useful for modeling. We have thousands and thousands of other points with little notes, maybe just a parent material, or, you know, there's a gate here, or a rock outcrop, or whatever. But we have 849 series level descriptions out there. And so I thought, well, there must be a way to use these. And right around that same time, I took a one-day workshop that was put on actually by the Forest Service, I think, about random forests. And I had heard of random forests before. I knew about supervised classification. I knew that, you know, decision tree-based modeling is something that people were doing for soils, but I wasn't familiar with it enough to actually use it. So it was a really good one-day class and helped me really understand what random forest is. And I'm not going to try to explain it all right now, but basically it's multiple classification and regression trees kind of working together using independent bootstrap samples of data, and at the end all of those predictions are combined into one class output map. And again, to be successful, it requires quite a bit of data, but I figured, you know, looks like we have quite a bit of data, so maybe we should give it a shot. And the other thing that I learned at the time, this is actually the first thing that we incorporated into our workflow, is that one of the outputs, or one of the tools within the random forest script that we were taught to use is this thing called variable importance. So one of the kind of first steps in the DSM process is figuring out which environmental covariates are important for the classes that you're trying to model and which data layers tie to those covariates. And there's literally hundreds of possibilities. And you know, there's lots of different ways to narrow them down. And we had been employing solely the method of us sitting down and like writing down what we knew about the soil classes and what we knew in terms of data layers and deciding which ones seemed to make sense. And there's absolutely nothing wrong with doing that. We still do it. But I was worried that we might be missing something, because I think that it's really easy to get, you know, stuck in your kind of bubble of what your favorite things are. And for us, that was slope and wetness index. Every model that we were running started with slope and wetness index. And I'm like, okay, maybe that's important for everything, but also there might be something else that's important. So we generated, I think, 26 data layers to start with. And again, for us, it's very terrain driven. But using the variable importance function, we narrowed that down to these data layers. So this is the start of the really pretty pictures portion of the webinar. The multi-resolution valley bottom flatness, relative position, terrain ruggedness index, and topographic wetness index all proved to be important via the algorithm, but they also had been, all of them except for the ruggedness index, had been identified by us as being important drivers of, or depicting the soil forming factors that drive where these soil classes occur for the ablation till parent material. So these are the data layers that were used in all levels of modeling. So these are used in the random forest predictions. They're also used in ArcSIE, and they are also used to help define sampling schemes. So this is the point data that we have for the ablation till parent material at this point in the White Mountains. So we have 340 points, I think. Again, these are ones that have a series description. And I broke them down into 3 groups. So the first thing that we did was take a small chunk, about 10 per class, out to save for case-based reasoning, to save for basically making the output of random forest better. So that's the 31 cases. Those are in yellow, I think. And then I split the rest of the points, 75% for model training and 25% for model validation. And so those 81 validation points are what are used for accuracy assessments for the model. And those don't get used at all as inputs into these algorithms, which is an important point when you take the DSM trainings. So I'm just going to go through kind of what it looks like. Again, with the pretty pictures, I will say that while we treat each parent material individually, we actually run these models across the whole area. So in case you're looking at this and you're like, why are you worried about ablation till results on what is clearly the top of a mountain? I'm not really. I've kind of trained myself to not even bother looking at those areas. But sometimes our parent material lines need to be adjusted and we don't want to have to rerun everything. But the key here is that ablation till LiDAR signature is anything that's really bumpy. So kind of right in the middle of this screen is a quintessential area of ablation till, and we'll zoom in on it in a little bit. But that's the kind of stuff that we're trying to model with this model. So this is the results from random forest class prediction, and this again, I don't have all the details of how many trees we did or anything like that, but this was using those 4 environmental data layers and the 231, I think, training points that every one of those training points was assigned to one of these classes, and random forest is able to say, okay, everywhere that looks like, acts like that class is assigned to that class in the output. And that's kind of the whole point of doing this. But these classes don't necessarily mean anything to anybody on this call except for maybe one person. But the key here is that the purple class is really underrepresented. So I was just like visually looking at the output, I was like, man, that needs to be adjusted somehow. And with random forest, using a completely machine learning driven method, I can't just, if I don't have any more data points in purple, I can't just, fix that. And there's a lot of things that happen kind of behind the scenes in the algorithm that I don't necessarily understand, but, it's a consistent result, but it may be consistently incorrect. So I was looking for ways to improve that. So here are some cases where random forest was incorrect, and those are some of those cases that are used in global case-based reasoning in the soil inference engine. So we are able to take those cases and feed them into the inference engine and get kind of another layer of places that look like those spots. Sometimes, since I set those points aside before running random forest, some of those cases already come out correctly, but some of them don't. But they're all used in this case-based reasoning, wherein you feed those into ArcSIE, and it is doing sort of a similar thing. I mean, all of these algorithms are looking at all those environmental data layers and saying, all right, where the conditions are the same as these points, then it's still that class. But the output from SIE are these fuzzy membership maps for each class. And so I looked at the fuzzy membership maps and decided that maybe I could combine those outputs with the random forest outputs to make an overall better map. And so the first, I'll say it's the first, I can't remember if it was the first thing that I did was assign everywhere on the map that had an 85 or higher fuzzy membership to that class. So let's say this is the membership map for that purple class. If it had a fuzzy membership of 85 or higher, that pixel was assigned to this class. And if it was lower than 85, then it was assigned whatever the result from random forest was. That resulted in a lot of purple, and I really like purple, but this was too much. So, so I went back and adjusted it and actually combined results of 95. In the end, I settled on a 95 or higher membership, fuzzy membership. If a pixel had a 95 or higher fuzzy membership, it was assigned to that class. If it was 95 or below, it was assigned to whatever came out of random forest. Sometimes it's that class, sometimes it's something else. And so this is the kind of final map. Final is in quotations because this is still a draft. But this is what it looks like. It does look totally messy. I get that this is a raster map and this is 1 to 24,000. And again, those ablation till areas are messy. It's a bunch of bumps. But again, we can be really quantitative about the work that we're doing. And so running accuracy assessments on this, and this is preliminary results. I hesitated putting this slide in here, but the random forest accuracy was hovering right around 58%. And that doesn't meet the standard. We have standards now for raster mapping, and it needs to be at least 60% overall accuracy, and I could potentially tweak it some more and get above 60%, but I took what was the best I could do at the time and incorporated those cases and brought the accuracy up to 74%. So while these may not be our final accuracy numbers, because there's a lot more that goes into this, I do think it's indicative of the kind of improvements that we can make to the results if we use some known point cases. So this is the last slide, and it's just going to quickly run through, again, the process, but zoomed in on that really bumpy area so you can kind of focus more on that. So it's, think about this area. I believe the scale of this is like 1 to 6,000. And in traditional mapping, we would draw a big blob around all of those bumps and call it one soil map unit, which is perfectly valid. But in raster mapping, we are able to pick out the differences between like what we know is the low wet stuff in between the bumps that are higher and drier, for example. So that's kind of the strength of raster mapping, is that we can actually differentiate between those conditions in an area that we wouldn't be able to do that at the scale of circle mapping. So this was the result from random forest. It's not bad, but you saw the accuracy number. It's not great either. So then we did some fuzzy soil inference and you can see how that really, those fuzzy membership maps really make the differences pop out between the bumps and the not bumps, for example. We made some adjustments. There is a ton of trial and error in basically any method of DSM. I think especially with soil inference, there's lots of opportunity for trial and error. It doesn't freak me out at all when I get a map that's like, whoa, what is this? So, we just keep trying until we get something that is reasonable, and that something is this at this point. And, one of the fun things about doing the GIS DSM work is that you get to play around and make things look the way that you want them to. So this looks really pretty, but it's also a more accurate representation of where these different soil classes occur. So that's it. I see there's some questions, so I am happy to answer them.
All right, Jess, thank you. I'll just remind people that you can enter a question in the chat or the Q&A, and we'll go through those and get to as many as we can. So the first one up, Jess, Taylor asked, what would be your preferred or cutoff accuracy for a finished product?
Well, the cutoff accuracy according to the standard is 60% overall accuracy. That seems really low, but when you talk about modeling a natural system, it's actually pretty good. And depending on how many classes you have, it can be a hard target to hit. My preferred accuracy is like 95, but that's nearly impossible. A lot of times you'll have a class or two that performs really well and a class or two that, for whatever reason, maybe it's just a small acreage size, so it's not well represented in your training data. There's usually always a class or two that performs really poorly, but is still important in the map, so that can bring your overall accuracy down.
All right, then there's a guest that's asking about the scale of 1 to 24,000. Can you speak to that?
Yeah, that was just, like I was zoomed in at 1 to 24,000, not it's 1 to 24,000 mapping. It is 10 meter pixels. All of this, actually it's 5 meter pixels, but it's published at 10 meter pixels.
And is this analysis still running in ArcGIS desktop, or have these tools been ported to Pro?
Well, the random forest is run in R, and ArcSIE is in the process of being ported to Pro. So currently it's still in ArcGIS desktop, but we are working on Pro as we speak.
And Taylor has a follow-up question. When this is ready to be published and uploaded to Web Soil Survey or a future raster Web Soil Survey, how will information be displayed? Based on class, series, interactive?
Well, that's a loaded question. It will be based on class. Every DSM project, a classification project, you define the classes that you can model. Sometimes those are series-based classes. Sometimes they encompass more than one series. We try to make it as narrow a definition as possible, but sometimes that's not, sometimes we just can't get down to the series-based component level. I look at it as especially here in a terrain-driven model, we are really modeling chunks of the landscape. Landform position is a huge driver, so the classes are really based on that. So your class definitions may vary. As far as when it's on a future raster web soil survey, the hope is that we will be able to display whatever that class information is, along with the uncertainty and accuracy data that goes along with it. And hey, interactive sounds great. I don't build that type of tool though.
And Edwin says, very good project, but he has a question. When looking at the areas that Random Forest gave a wrong result, is that related to any outlier data points where you could have a data point in an atypical location, or maybe related to scale?
Yeah, that definitely could be the case. This current draft of this anyway, I did not remove any outliers. I think once you start weeding out your data, you introduce a whole lot of bias really fast, and sometimes that's appropriate and sometimes it's not. This is still in the kind of test phase of, is this worth really adopting for the rest of the project? So I wanted to make sure that I wasn't introducing too many variables like that by weeding through the data. And again, that's one of the things, we're constantly trying to balance the academic and operational approaches to this. And some people would argue, never mess with your data. Of course there's outliers, but don't take them out. Other people would say, get rid of anything that's not typical and go with that. I try to strike a balance between those two.
All right, and Burr has some questions. He says, he talks about, how you mentioned the theory of Jenny is taken into consideration, but what types of data do you feed to the machine? And he says, assuming climatic and soil properties in all the horizons, can you speak to that part again?
Sure. The kind of data that the covariates that we are talking about are terrain and spectral driven derivatives. So for us, that's the things like wetness index or ruggedness. They're outputs from that are based on elevation data. You can use all kinds of input data. I mean, as long as it's something that corresponds to your definition of the soil landscape relationship, you can use it. People use temperature data if it makes sense to do that. I don't, as far as like horizon-based data, that gets pretty complicated pretty quickly. The key is that as far as soil class mapping goes, the computer can't see underground, and usually, especially not in a initial soil survey, we don't have enough horizon-based data to be able to build that kind of model anyways. It's really more about things that help us tell the story of the soil forming environment, and something like wetness index in certain materials corresponds really well with drainage class. So, we may define classes based on drainage class, and that wetness index isn't a drainage class map, but it acts as a proxy for that, so we can use that to drive the results of the model. If that makes sense.
Jess, I would also add to that the point data, when you incorporate point data into your modeling, which is done either indirectly or directly in all classification methods, but that is a representation of soil properties that you're trying to capture in your classes.
Yep.
This next one may be kind of a confusion on when we use the term classification, but the question is, how much time do you save using this technique compared with conventional classification, and will you be able to classify at the soil order level?
Yeah.
So the question may be more, how much time does this technique save over conventional mapping?
Right, which is kind of hard to answer, honestly. It changes how and when we do mapping. We map year-round now because we do a lot of the model work in the winter, and then we're out in the field in the summer checking it. It doesn't take away. In fact, I would say it might have even added field work to it, but it has changed it. We instead of traversing the landscape, we are going to specific points. I don't think I said this when we were looking at the distribution of points, but all of our field work it's done for multiple purposes and in multiple ways. So we have a bunch of directed investigation where we're trying to figure out soil landscape relationships, and then we have classified random sampling that has supported various projects that have been going on in the forest, and then we have condition and hypercube sampling. So anyway, we spend a lot of time in the field, but it's just time spent a little bit differently. And then there's still all the database work. So I hesitate to say that doing it this way makes things faster. I think you can certainly employ DSM methods to make a map faster, but it really depends on your classes that you're defining and how accurate you want to make the map. There's a lot of variables to that.
All right, Bernie has a question. What is the order of mapping?
That is irrelevant to a raster-based map, but the Sergo mapping will be probably a combination of order 2 and order 3.
And Glenn has a question. Does the current raster accuracy standard meet the user's needs in the White Mountains?
Good question. Yes and no. I think, again, the standard of, it's a pretty simple standard of overall accuracy of 60%, which again sounds kind of low, but like I mentioned before, I think that most of the classes will perform much better than that. And so for the most part, that will be perfectly fine. And it's hard to compare Sergo to raster in terms of which is more accurate, but we, our main customer, of course, is the Forest Service, and they have said that they want as close to a component level raster map as possible, and so that's what we're doing for them. And we can be transparent about how accurate that is. That's a strength.
All right, and a guest asks, are the scripts and data available to use as practice material?
The scripts, yes. The data, I mean, I could share it with you, sure. If you take the DSM classes, all of this stuff, the techniques and scripts and all of that, and as well as practice data are kind of included in that. The ArcSIE software, it's arcsie.com. You can download it for yourself. It's already loaded on, it's an extension of ArcMap, and it's already loaded on most soil scientist machines.
All right, and Taylor has questions. If you start a DSM project from scratch, do you still use the traditional Catena map unit design approach? And how does the data input into NASA's change with a raster product?
I would say that it's probably a slightly different map unit design approach, especially because we, anyway, generally focus our target classes around a soil series as much as we can. DSM, you can model series-based classes or go straight for map units. It's really more about trying to quantify that soil landscape relationship, and I just think that raster maps are a little different than Surgo conceptually. But we do go with the Catena-based approach, and that's why we treat each parent material separately and really try to, think about the classes, Catena-based classes within each parent material. As far as the NASAS goes, again, it kind of depends on what those classes end up being, but it's the same kind of data entry. And we have a different example, but the Essex County product, those were single component map units, but the components were not necessarily tied to one series. They kind of, the range and characteristics was broader than a one series component. So it's just slightly different. It can be, anyway, slightly different way of capturing the data. The key here is that we have tons of georeference data, and we do our very best to make sure that the range and characteristics in those map units are reflective of actual field measurements.
All right, Nathan has some questions. How do you do your accuracy assessments? Are you counting name-dominant map unit components, or do you consider name-dominant components and similar soils as a success in terms of accuracy?
So we do the accuracy assessment based on the classes that we are predicting. So, I save out a bunch of points that don't get used in model training, and using, GIS tools, we can compare the values, the class that we found in the field to the class that was predicted, and that's the accuracy numbers that you see. And so one of the variables that, depending on your accuracy tools that you're using, you can look at just that one pixel and say yes or no, we hit it or we didn't hit it. But you can also look at surrounding pixels and say, all right, we were close to hitting it. This was just pixel to pixel. This point falls in this pixel, and we saw class 1, but the prediction was class 2, so we were wrong, for example.
And there are other methods of measuring accuracy that include accounting for class similarity. So those are an option.
Yep.
So Luis has a question I know it's come up many times before. Are we using this approach in other parts of the country, like flat landscapes?
Yes, I don't know if anybody's using exactly this approach, but yeah, DSM in general is being used all over the country. There are different, you would use different covariates in a flat landscape versus this one. We don't use spectral data in our model, not to say we couldn't, but a lot of times, and I see Martine has said yes in Florida, so we just had a DSM field week down in Florida, basically flat as a pancake, so spectral derivatives are a much more important part of the model down there than they are here because the vegetation is a larger indicator of the soil environment than it is here.
All right, well, it looks like that's exhausted our questions. So thank you to Jess and Suzanne for your time and effort to make this presentation. And thanks to all the participants for joining in. We hope you found this information beneficial. We had more than 200 people join today's webinar. As I mentioned earlier, a recording of this webinar will be available on our National Soil Survey Center YouTube channel within a couple of days. So please feel free to let your colleagues know about this training opportunity. And this concludes our webinar presentation.